So now that we've explored the Bohr model and have done some drawings, I want to remind you that our drawings are not exactly accurate. The distance between energy levels changes. The energy levels keep on getting closer and closer. So the distance between N1 and N2, that has a much larger energy drop than the distance between 7 and 6. So when an electron falls from 7 to 6, it does not give out anywhere near the amount of energy as if an electron would drop from 2 to 1. And when that electron drops, it gives off a photon, which gives off energy in the form of light. This energy is the photon. And so we can calculate a lot of things about light. First of all, if we know the frequency, we can calculate the wavelength. So wavelength and frequency, again, are inversely proportional. When one goes up, the other goes down because they always have to equal this constant, which is the speed of light. So here is an example of the equation. You need to rearrange it if you're solving for frequency right here, and you should know how to rearrange that using algebra. And then you just plug in your numbers. A note, remember, if you want any credit on your work, you have to show me the formula rearranged, the numbers plugged in, and then your answers with the correct unit. So we can also figure out, based on wavelength or frequency, the type of energy. So we had these two formulas. We have the energy, the photon, is the frequency times Planck's constant, okay? And then frequency times wavelength equals the speed of light. So if we rearrange and substitute back in for V, we can get the energy of that photon related to its wavelength. And H is Planck's constant. That's a constant that's given to you. Okay, so actually, I have Planck's constant down here, just so you know. So here is a problem. What is the energy of a blue light that has a wavelength of 450 nanometers? So here's our equation. We plugged in these numbers, and you may notice down here we have 1 times 10 to the negative ninth. Why is that? Well, if you look at our units, our energy is in joules. Our Planck's constant is joules per second. And here our speed of light is meters per second. So meters has to cross out. So if we're given nanometers and we're using the speed of light, we need to convert it to meters. So they did that right inside the problem. Feel free to convert your nanometers to meters separately, or you can put it all together just like this. So another type of problem you will see that's going to relate our energy to our Bohr model is going to actually go off of these models right here. This is the cutout of our Bohr model. You can see here is our shells, and here's energy level 1. Our nucleus is down here. Our big jump going to the next energy level on our Bohr model. Here's the cutout. We go to the next energy level. Now, what they've done here is they've put in the energy. So another unit for energy instead of joules is called electrovolts. And super fun for you, we have another conversion, okay? Electrovolts can be converted to joules because 1 electrovolt equals 1.6022 times 10 to the negative 19th joules. So you will have to do those conversions. So if my electrons dropping from N2 to N1, the energy it's given off is the delta E, which is the difference between those two energy levels. So 11.2 minus 1, it gave off 10.2 electrovolts. And I did that calculation right here for you. Okay, it's the difference between these two. Much less energy is given off when I go from a higher level energy, and I just dropped down one energy because they're closer together. So when I go from N6 to N5, that's only 0.2 electrovolts. That's because these energy levels get closer and closer together, so the distance it's falling in the model is a little shorter. It's giving off less energy. So how can you determine the type of light that's given off when an electron drops from N2 to N4? This is a complicated problem. First of all, we need to find out the type of light, and we can find that from our wavelength, okay? And we have this equation. We can figure out the energy of a photon using this model up here, but it's in electrovolts. And since our Planck's constant is in joules per second, our energy has to be in joules. So first we're going to rearrange the formula because we're solving for wavelength to figure out the type of light. And a reminder of your constants: C is the speed of light, H is Planck's constant. Those numbers never change. They're given to you. Determine the energy from N3 to N2. So that needs to be fixed. Let's fix that. N4-N2. Okay, so if I go to my handy dandy model here, N4 is 13.8 electrovolts and N2 is 11.2 electrovolts. I just subtract those and I get 2.6 electrovolts. Okay, now the energy has to be in joules, so I have to convert that electrovolt to joules. I don't want electrovolts, it goes on the bottom, and what I want is joules, it goes on top. And then I get this amount of joules. So now I have Planck's constant, always a given number, speed of light, given number, my energy, I just figured out in joules, and I can plug that all in. And the only thing you need to be aware of is because our speed of light is meters per second, we have solved for meters. Notice my joules cancel out, joules, joules. My seconds cancel out, seconds, seconds on the bottom. I'm left with meters. Our wavelengths here and our light is all done in nanometers for the visible spectrum. And so, since this is in that area, I'm going to convert my meters to nanometers, and that comes out to 477 nanometers. This is your metric conversions, and 1 times 10 to the negative 9th meters is 1 nanometer. So I get rid of meters, I put it on the bottom, put my nanometers on top, and when I look at my electromagnetic spectrum, 477 nanometers is in the blue range. So this corresponds to blue light. And you will be practicing these calculations on a worksheet right now.